Okay, in this section we're going to be solving trigonometric equations. So, what the heck is a trigonometric equation? Well, it's an equation with trigonometry in it. And we should go right into our first example. Okay, so this is a trigonometric equation because it's an equation and it has at least one trigonometric function, cosine of x here. So we're looking for the x values that make this equation true. So the solutions to this equation will be one or more angles that when you take the cosine of that angle and double it and add 1, you get 0. So yeah, how do we solve a trigonometric equation? Well, your first job is simply to isolate the trigonometric function. So we're just going to isolate cosine of x. Okay, so here's the original equation. And to isolate cosine of x, we'll subtract 1 from both sides. And we'll divide both sides by 2. Okay, so we have succeeded in isolating cosine of x. Okay, once you have the trigonometric function isolated, the next thing to do is to list the solutions that are between 0 and 2 pi. So basically, these are the angles in the unit circle from 0 to 2 pi whose cosine value is -1/2. Now, I like to visualize this with a chart of the quadrants. So we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And let's first determine which quadrants will have an angle whose cosine is -1/2. So since -1/2 is, of course, negative, we have to rule out any quadrants where cosine of an angle is positive. So we know we're going to rule out quadrant 1 and we're going to rule out quadrant 4. So this means that in quadrant 2, there's an angle whose cosine is -1/2. All right, well, this entire section is going to heavily depend on your knowledge of the unit circle. We know that cosine of 2 pi over 3 is equal to -1/2. Okay, and in the third quadrant, there's also going to be a solution, and we know that cosine of 4 pi over 3 is -1/2. So the individual solutions between 0 and 2 pi are 2 pi over 3 and 4 pi over 3. Now, many of your homework questions will simply ask you to only list the solutions between 0 and 2 pi, in which case we have our answers and we'd be done the problem. However, if it doesn't specify that you're only listing solutions from 0 to 2 pi, then we actually have to write all the solutions. And there's actually an infinite number of solutions, because everything coterminal to 2 pi over 3 is a solution, and everything coterminal to 4 pi over 3 is a solution. For instance, we know that cosine of 2 pi over 3 is -1/2. Now, if we added 2 pi to that, we would get 2 pi over 3 plus 2 pi, whatever that is. And the cosine of that is also -1/2. So x equaling that particular angle is a solution to this equation, but we haven't listed it. In fact, you could go around 10 more times, right? And that would be adding 10 times 2 pi, so 20 pi, added to this angle. And you would, of course, land right here. And the cosine of that angle is -1/2. So whatever that number is also a solution. So there's an infinite number of solutions. And this also applies to adding multiples of 2 pi to this solution, 4 pi over 3. So even if a question says find all solutions, you still have to start by listing the solutions between 0 and 2 pi. Then what you do is you write down all solutions in the following way. We say that x is equal to, say, 2 pi over 3, one of our primitive solutions that we found from 0 to 2 pi. and then we say plus 2 pi n. And we stipulate that n is an integer. That's what this notation means. So what this statement here says is it says 2 pi over 3 is a solution, as well as 2 pi over 3 plus any multiple of 2 pi. And we also have to capture the 4 pi over 3's. So 4 pi over 3 plus, again, everything coterminal to 4 pi over 3. And this, along with the stipulation that n is an integer, represents the infinitude of all the solutions. So anyone interpreting your solution can choose any n value that he or she wants and generate specific answers. So for instance, if we were to let n equal 0, well, that would eliminate this term and this term, and that would actually give the pair 2 pi over 3 and 4 pi over 3. If you were to let n equal 1, then you would get the solution here, 2 pi over 3 plus 2 pi times 1. So it's like going around an extra time and still landing on 2 pi. And you could even let n be negative 5, which is like starting at 2 pi over 3 and then going clockwise 5 times around the unit circle and still landing again at an angle coterminal to 2 pi over 3. And that would indeed be a specific solution. All right, here is a visualization of the equation that we just solved. Now, the equation was 2 cosine x plus 1 equals 0. So in order to get Desmos to graph it, we had to replace 0 with y. But the solutions to that equation would just be exactly where y is equal to 0, which would be the x-intercepts of this graph. So we can see, first of all, that there are an infinite number of x-intercepts, corresponding, of course, to our infinite number of solutions. However, they fall in a very regular pattern. So again, the way we solved this equation was we first looked for solutions between 0 and 2 pi. And that corresponded to these two x-intercepts. We got the solution of 2 pi over 3 and 4 pi over 3. Now, of course, that doesn't account for any of the other solutions. But the other solutions are going to be based off of those two. For instance, if we added 2 pi to 2 pi over 3, which is exactly one period length of this function, that would get us to 8 pi over 3, which is this solution over here. Let me just turn the 4 pi over 3 off for a moment. So these are 2 pi apart. We could also subtract 2 pi from 2 pi over 3, and that would have given us this particular solution of negative 4 pi over 3. So notice that if we just keep adding 2 pi, we'll find more and more solutions. So that's why we can state this particular family of solutions as the original one, 2 pi over 3, plus an integer multiple of 2 pi. Of course, this particular statement does not capture the other set of infinite solutions. So that's why we independently write that 4 pi over 3 is a solution, and plus every multiple of 2 pi off of that. So taken together, we account for every single x-intercept of this graph, or every single solution of the original equation. And this is why we're going to see that the solutions to a trigonometric equation will take on a form that looks exactly like this. Okay, so let's get into some more examples. All right, let's solve this particular equation, and this time we're going to solve it in degrees. So you should know that I'm adopting your textbook's convention here that when an equation is presented with x as its variable, the implication is that we're solving in radians, and when theta is given as the variable, the implication is we're solving in degrees. So here we have theta in the equation, so we're solving in degrees. Okay, well, mechanically that doesn't really change our approach. We're going to start by isolating the trig function. So in this case, that's tangent of x. All right, there's the original equation. So let's start by adding the square root of 3 to both sides. And now we have this. We'll just divide by 3 on both sides. And that will have tangent isolated. Okay, once you have the trigonometric function isolated, the next thing we do is we list the specific solutions between 0 and 2 pi. Although here we're solving in degrees, so it'll be 0 to 360 degrees. All right, so again, we have the quadrants here, and let's see which quadrant will produce a solution. So tangent is rad 3 over 3, which is positive. So we need to rule out the quadrants where tangent's not positive. So tangent's negative in the second quadrant, and it's negative in the fourth quadrant. So we know there's going to be a solution in the first and the third quadrant. So again, just appeal to your intrinsic unit circle familiarity to answer these questions. What angle in the first quadrant has a tangent value of rad 3 over 3? And that is 30 degrees, or pi over 6, if you're working in radians, but we're not. Okay, so what about in the third quadrant? Well, it's just going to be whatever angle's in the third quadrant that has a reference angle of 30 degrees. That would be 210 degrees. Okay, so in the interval 0 to 360 degrees, the solutions are 30 degrees and 210 degrees. And again, if the question had asked just to list the solutions from 0 to 360, as many of them do, that would be where we stop. But it's not hard to go one step further. So if we wanted to list all solutions, we would say something like theta is 30 degrees plus 360 degrees n, where n is an integer. Okay, also 210 degrees plus everything coterminal to 210 degrees. So this adding 360 degrees is equivalent to adding the 2 pi, right? Except it's in degrees, of course. Okay, very good. So this is not incorrect, but we are missing a very important simplification that is necessary in this case to include. And that is simply the fact that we have some redundancy here. Notice that 30 degrees and 210 degrees are antipodal, meaning they're pointing in exactly the opposite direction. So they're evenly spaced. So consider this simplified version. What if we said the solution is 30 degrees, and instead of adding 360 degrees, we just added 180 degrees times n? That would actually capture both the 30 and the 210 and everything coterminal to both of them in one little statement. Because we have the 30 degrees, and then we add 180, that gets us to the 210. Then you add another 180, it gets you back over here to something coterminal to 30. Well, then you add 180 again, that gets you over here to something coterminal to 210. And you can just keep doing that back and forth, and you're actually going to catch everything. So this is why I think it's very important to draw a chart of the solutions while working them out and not just merely listing them. Because with the chart, you can start to see that some of the solutions might be evenly spaced, as they are here, and then you can reduce your answer to a single line, as we have. All right, so again, here's the graph of the function y equals 3 tangent of x minus rad 3. Of course, we had to change theta to x in order for Desmos to handle it properly, and also this is in radians at this point, but we know how to convert back and forth. So once again, the intercepts of this function are going to be the solutions. And we have one right here, and that's the pi over 6 that we found, which is 30 degrees, and 7 pi over 6, which is the 210 degrees. And notice that all the solutions are perfectly evenly spaced apart, and they're all 180 degrees apart from each other, or pi, right, in radians here. And that's why we could just simply write the first solution and add any multiple of pi to it. Or again, in degrees, that would be 30 degrees plus a multiple of 180 degrees, which is equivalent to pi radians. All right, here's a situation where we have more than one trigonometric function. And by that, I mean we have cosines and cotangents. So isolating one of them would involve simultaneously not isolating the other one, right? If we had cosine on the left equals stuff, that stuff's going to still have cotangent of theta. So when you have more than one trigonometric function, like we do here, you basically have two options. One is to try and use identities to convert one of them over to the other. So for instance, maybe try and turn the cotangent into cosines or vice versa, so that you have only cosines, and then you can just isolate cosine of theta. The other option is to move everything over to one side and try to factor. And that's what's going to work here. So let's do that. All right, so here's the original equation. So let's add cosine of theta to both sides. So we have cosine of theta, cotangent of theta, and now plus cosine of theta is equal to 0. And now you can see that we can factor because we have two terms and they have a cosine of theta as a common factor. So if we factor the cosine of theta out, we'll have cosine of theta times cotangent of theta plus 1 is equal to 0. Now we can use something called the zero factor property or zero product property, where if you have two quantities multiplied together equaling 0, and you're in the middle of solving an equation, you get to separate and say, well, one or both of them is equal to 0. So in other words, we can split this and say we have the equation cosine of theta is equal to 0, and we have the equation cotangent of theta plus 1 is equal to 0. Now, this splitting process, I want to remind you from algebra, only is valid if the right-hand side of the equation is equal to 0. If you don't have 0 on the right-hand side, you can't do this. You have to continue to move terms over to the left and then refactor everything with what's new there. So here we do have 0, so this is perfectly valid. And good news, because now both of these much smaller equations have each only a single trigonometric function, so that's awesome. We can just, isolate each one. Of course, cosine of theta equals 0 is really already isolated, but on this one, if we merely subtract 1, we will get cotangent of theta is equal to -1, and awesome, now they're both isolated. Okay, so we're going to proceed as we have been. And that is first by listing the solutions between 0 and 360 degrees. We are solving in degrees because we're using theta here. Okay, and as you know, my recommendation is to draw a chart of the quadrants and individually mark the solutions. So, okay, let's start with cosine of theta equals 0. So what are the angles between 0 and 360 whose cosine value is 0? Okay, well we know that cosine of 90 degrees is equal to 0. And we also know that cosine of 270 degrees is equal to 0. Okay, very good. That's it. Now we'll put our attention on this other equation. Cotangent of theta equals -1. Well, we can see that cotangent is negative. So where is that possible? Well, that's not possible in the first quadrant, and that's not possible in the third quadrant. So we know that there's going to be a second quadrant angle whose cotangent is -1, and the same is true for the fourth quadrant. Okay, well, in the second quadrant, we know that angle is right in the middle here, and that would be an angle of 135 degrees. And in the fourth quadrant, it will be the angle with the same reference angle. It's a reference angle of 45 degrees, and that would be 315 degrees. So these four solutions are the four solutions to the original equation that are between 0 and 360 degrees. Okay, but now let's just list all of the infinitude of solutions. Now it would be quite a chore to write theta is equal to 90 degrees plus 360n. Theta is equal to 135 plus 360n, etc. Well, it wasn't a huge chore because I just did it in a few seconds. But it's also very inefficient, and that is because we can take advantage of some of the uniform spacing that we can see on our little star chart right here. So let's first note that they're not all evenly spaced, because this is a gap of 45 degrees, but this is a gap of 135 degrees. So since they're not all perfectly evenly spaced, we will not be able to get it into a single statement. However, what we can do is say that theta is 90 degrees plus 180 degrees times n, and that captures the 90, of course, but also the 270, which is exactly 180 away from it. And then when you add another 180 to that, you go back up to the top here, to the one that's coterminal to 90. And you add 180 to that, and you're back down here to something coterminal to 270. And you just bounce back and forth. So those two arrows are covered by this statement. And we can, with one more statement, capture the other two. And we'll just say 135 degrees plus 180 degrees times n. Of course, always have to stipulate that n must be an integer. And there we are. This combined statements here constitutes the full set of solutions to the original equation. Okay, here's another equation, and this time we only have one trigonometric function, so that's awesome. It's in x, which means we're solving in radians. So yeah, let's dig in and see what's going on here. Let's start by isolating sine of x. Okay, of course we'll subtract 1 from both sides, and we'll divide both sides by 3. So we get sine of x is equal to negative 1/3. So now we're going to list the solutions that are between 0 and 2 pi. All right, so of course we've been relying on our unit circle knowledge to get through this part of the problem. But the problem in this case is that negative 1/3 is not one of the familiar ratios for sine that we know and love. Like it's not 1/2 or rad 3/2 or 0 or 1 or, well, anything that we normally see for sine of x. Well, what that means is we're going to just have to use the inverse sine function when the time comes, and we'll be stuck with a decimal approximation answer. That's no problem. All right, so we still need to project what the quadrants are where our solution is. So we have sine of x being negative. Well, that's certainly going to rule out the first quadrant, and it's going to rule out the second quadrant. So we know that there's going to be a solution in the third quadrant and a solution in the fourth quadrant. All right, so how do we find them? Well, let's find the inverse sine of negative 1/3, because this question's like asking, hey, what angle has a sine value of negative 1/3? And the inverse sine function is what we use to answer a question like that. So first of all, let's make sure that we're in radian mode, because this is a question in radians, and now we'll evaluate inverse sine of negative 1/3. And this specifically comes out to negative 0.339836909. Well, there's a problem with this, and that number is negative. It's not even in the range 0 to 2 pi. We are specifically looking for some unknown third quadrant angle and some unknown fourth quadrant angle. And they're both supposed to be positive because they're both angles between 0 and 2 pi. Well, remember, if you give a negative ratio to inverse sine, it's going to generate a negative fourth quadrant angle. So what we have here is actually this negative angle right here. There's our negative 0.339 radians. Now what we really want is this positive angle that's coterminal to it. So what we're going to do is add 2 pi to our answer, and that's the angle we want here. So this specific one right here is 2 pi plus what we calculated for inverse sine of negative 1/3, which is 5.943348398. And that actually continues on forever. Remember, 2 pi itself, numerically, is about 6.28, right? Because pi is 3.14. So a fourth quadrant angle is very often in the form of 5 point something. And this would be our positive fourth quadrant angle right here. Okay, but the real question is, how the heck are we going to find this third quadrant version of that angle? Well, we know that this reference angle must match this reference angle. And remember that this value here was negative 0.339. So that's a reference angle of positive 0.339 blah 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 blah. So all we have to do is take this amount right here, which is pi, and add 0.339 blah blah blah, right? So okay, well, how do we do that calculation? That's going to be pi, and we want to add the positive version of this number right here. So why don't we just subtract that number? So that's going to be like pi minus the inverse sine of negative 1/3. Well, that's something we can actually calculate, and that comes out to 3.481429563. All right, so those are the individual solutions between 0 and 2 pi. So we'll just list them. And if we want all solutions, it's just going to be each of these weird solutions plus everything coterminal to them. Now, there's no hope that these are evenly spaced, so we're just going to need two independent statements. And we'll say that x is equal to the first one, 3.4814, plus everything coterminal to it, and x is equal to the other one, 5.9433, plus everything coterminal to it. Again, stipulating that n is an integer. Okay, now when you've done a process like this, where you've had to do a lot of deep calculator work, it's often a good idea to check your answer. So why don't we actually check this one? Is it true that if we take 3.4814 and plug it into the equation for x, do we get 0? All right, let's try. So I just checked this on my calculator, and because we didn't use all the digits, we got a number very, very, very close to 0, but that's enough to convince me that we're right. All right, so here we have an equation, of course. It's only got one trig function, which is sine of x. Of course, it appears multiple times. But notice that we have sine squared here and sine to a first power. So this is a form of an equation, of course, known as a quadratic equation. All right, no problem, because we know how to solve quadratic equations. So yeah, let's start by isolating sine of x. Now, recall to solve a quadratic equation, you get everything on one side, so it equals 0, which, well, it's already in that form, so that's good. And once you've done that, then you want to try and factor the left-hand side. And if it doesn't factor, of course, then you go to the quadratic formula. So yeah, let's try to factor this. Now, you may find that trying to factor this is a little distracting with the fact that it's a sine of x and not just a single variable. So a neat little trick is to quickly make a substitution where we're going to let u equal sine of x. And that means that sine squared is u squared. Of course, sine of x is just u. And we have this equation. So we're just going to factor this with a u in it instead of with sine of x. And sometimes just looking at it like this kind of activates our algebra minds a little bit better than the original form with the sine of x's that were very distracting. So does this one factor? Yes, it does, doesn't it? Just like that. Okay, and again, using the zero factor property, we can split this into two independent equations. Very good. And now remember, u was sine of x, so we can go back to writing this in terms of sine of x. And we'll just quickly finish solving each one of these equations. So on the left here, if we subtract 2 from both sides, and then divide both sides by 3, we get sine of x is equal to negative 2/3. And over on this side, all we have to do is add 1 to both sides, and we get sine of x is equal to 1. So finally, we have succeeded in our task of isolating sine of x, because we have sine of x equals stuff, right? Sine of x equals stuff over here too. So now we're going to list the solutions that are in 0 to 2 pi. Again, we're working in radians because the variable here is x and not theta. Okay, so sine of x equals negative 2/3. Let's come back to that one. Let's go over here. Sine of x equals 1. That one's very easy, right? There's only one number between 0 and 2 pi whose sine value is equal to 1. And that is right here at pi over 2. All right. I guess now we have to deal with this one. Sine of x equals negative 2/3. So we're in kind of the same situation we were in the last example, because negative 2/3 is not one of our well-known ratios like rad 3 over 2 or 1/2 or whatever for sine. So this means, again, we have no choice but to do what we did last time, which is invoke the inverse sine function. And as we know, it may or may not actually be part of our specific solution. So let's just work it out on the side. So inverse sine of negative 2/3 is negative 0.729727. And there's more stuff after, but who cares? Okay, returning to our quadrant chart here, we should determine what quadrants will produce a solution. So we can see that sine of x is negative. So that does rule out the first quadrant, that rules out the second quadrant. So again, just like last time, we're going to have kind of some unknown solution here and some unknown solution here. So the fourth quadrant one's probably the easiest to get based on our inverse sine calculation. Again, all we have to do is add 2 pi to that. So I get an answer of 5.55 and other stuff. Okay, and again, the third quadrant solution is a little bit trickier, but we do know that it shares the same reference angle as the fourth quadrant solution. So that reference angle is just the positive version of that negative 0.7. So if we just take pi radians and we add the positive version of this number here, then we're going to get this unknown number right here. So this is going to be like subtracting pi minus that negative. So on a calculator, I got this is 3.8713231. All right, so in the interval 0 to 2 pi, the solutions are these three angles. Now, one of them is like normal, pi over 2, and the other two are like very strange. So we'll just write them in here. We'll round them to 4 decimal places. So 3.8713 for that first one, and the other one 5.5535. And there's no chance that these are evenly spaced. So we're going to just have to write this in 3 independent statements. So the first one, very nice, is pi over 2 plus everything coterminal to pi over 2. The next one would be, of course, this thing plus everything coterminal to that, and this one plus everything coterminal to that. Once again, stipulating that n is an integer. Okay, this one was pretty weird, so let's look at a graph of that one and see if anything that we did makes any kind of sense. Okay, well, this interesting wave is the graph of this curve here, and obviously the solutions to our equation will be where y is equal to 0, as usual, so that'll be the x-intercepts. And we found that the solutions involved pi over 2 plus everything coterminal to pi over 2, so of course 5 pi over 2 and so on. So if we added 2 pi and just kept doing that, we'll get all of them. All right, but we also found some pretty weird ones. There's the 3.871 and everything coterminal to that, so that would be the next one, adding 2 pi to it, and then there'd be another one to the right. And we also found this family, the 5.553, and this one here adding to that. And in fact, if we subtract 2 pi from it, we would get this, which was what we originally calculated when we took the inverse sign of -2/3. But we couldn't list it specifically because that particular point is not between 0 and 2 pi. Only these 3 points are between 0 and 2 pi. Okay, here again we have two different trigonometric functions, a cotangent and a cosecant. So we can't just isolate the trig function like we normally do because there is no the trig function, right? There's two of them. This means we either need to move everything to one side and factor, or we need to try to find identities to connect one in terms of the other. The problem is if we move them all to one side, like let's say we move cosecant over, well, how the heck do we factor this? That's not to say that this doesn't factor at all, but let's consider an approach involving identities. So what's an identity that connects cotangent and cosecant? Well, we know the one coat in the closet identity, right? 1 plus cotangent squared is cosecant squared. So we could use that, but the problem is these are not squared. So that's not really a problem because we have an equation here, and you can do whatever you want to an equation as long as you do it to both sides equally. So let's start by squaring both sides. Okay, so here's the original equation. And now let's square both sides. Now, the left-hand side is a binomial, meaning it's got two terms in it. So to square it, we're going to need to use FOIL. So that's going to give us the form of cotangent squared minus 2 times the product of these two things, so 2 rad 3 cotangent of theta, and then plus the square of rad 3, so that's just going to be 3. And squaring cosecant of theta is, of course, just cosecant squared of theta. Okay, yeah, so this doesn't look that great, except for the fact that we now have a cosecant squared, and we can rewrite this as 1 plus cotangent squared. And it's true that we're going to have somewhat of a mess at that point, but at least we have only one trig function, which means we can isolate it algebraically, which is our goal all along. So this is... Okay, this doesn't look great, but it actually is pretty good, because right away we can cancel cotangent squared from both sides. So what we have is -2 rad 3 cotangent theta plus 3 is equal to 1. Great, let's just keep isolating till we have cotangent theta by itself. So we'll subtract 3 from both sides. 1 minus 3, of course, being -2. And now we'll divide both sides by the coefficient of cotangent theta, which is -2 rad 3. So the -2's cancel. And what we get is cotangent of theta is positive 1 over rad 3, or rad 3 over 3. Hey, that's a thing we know how to deal with. In fact, if you prefer, you can write this as tangent of theta is equal to simply rad 3. Because personally, I speak the language of sine, cosine, tangent a lot easier than I speak the language of, cosecant, well, the other ones. So pretty much all we have to do is find the theta values, of course working in degrees right now because this is theta, whose tangent is equal to rad 3. Well, we should all be able to do that. So let's finish this and go home. Okay, so tangent of theta being positive here means that we're expecting a solution in the first quadrant, but not the second, and yes on the third, but no on the fourth. So let's put our attention on the first quadrant. What angle in the first quadrant has a tangent value of rad 3? Well, that's 60 degrees. And in the third quadrant, it'll be whatever the angle is that has a reference angle of 60 degrees. So of course, that would be 240 degrees. Okay, so at this point, we usually say something like the solutions in 0 to 360 are, and we just list the ones we found, 60 and 240. But there's a big problem here, and it's a problem we haven't encountered until this particular problem. We don't know that these are actually both solutions to the original equation. Now, why is that a problem here and it wasn't a problem before? When you square both sides of an equation en route to solving it, you introduce the potential for false solutions. So if you square an equation, you're forced to just manually check each solution. And you must check them in the original equation. Okay, so let's check the 60 degrees solution. Is it true that cotangent of 60 degrees minus rad 3 is equal to cosecant of 60 degrees? Okay, well, cotangent of 60 degrees is rad 3 over 3. So is this left-hand side equal to cosecant of 60 degrees? Well, cosecant of 60 degrees is the reciprocal of sine of 60 degrees. So this is going to be 2 rad 3 over 3. So is this true? Well, we need a common denominator over here. So now we have everything over 3. Let's do the subtraction. Rad 3 minus 3 rad 3, that would be negative 2 rad 3 over 3. Is that equal to 2 rad 3 over 3? No. So 60 degrees is not a solution. All right, let's try the other one, 240. Is cotangent of 240 degrees minus rad 3 equal to cosecant of 240 degrees? Okay, well, what's the cotangent of 240 degrees? So 240 degrees is in quadrant 3, so cotangent's positive there. So this is going to be, again, rad 3 over 3 minus rad 3. And cosecant of 240 degrees, well, again, this is quad 3. Cosecant's negative in quadrant 3, so this is going to be negative 2 rad 3 over 3. And this left-hand side is still going to evaluate, as it did before, to this. And this time, we have a winner. So 240 degrees is a solution. Okay, so it won't always be true that one works and the other doesn't. It could be that they both work. It could be that neither of them work. So you just need to check each one. And in this case, we had the 240 working and the 60 not working. All right, so updating our chart here, we can see that the 60 is not a solution. So let's scratch it out. We only have the 240. So great, let's finish and go home. So between 0 and 360 degrees, of course, there's the singleton solution of 240 degrees. And if we wish to write all solutions, well, it's just going to be that 240 degrees plus everything coterminal to it. Stipulating, of course, that n is an integer.